discovery of plastic materials has contributed to the lifestyle of human beings in many ways. However, prolonged usage of these plastic materials cause adverse consequences to our environment due to the nature of their chemical compositions. Improper disposal of these plastic materials has led to waste problems, destroying our environment. For instance, a lone plastic bottle fully biodegrades after 450 years in our oceans. And this plastic bottle has a message for us. In that 450 years from now, that the new generation will live in, do we want our waste to be their future? No. That is why I'm here to present to you today a solution for this ongoing problem. Well, there have been several attempts to lessen down the degradation time of these petroleum-based plastic materials. These attempts, however, have not been fully successful yet or too expensive to set out in the market on a consumer's daily basis. A new era dawned in the 1800s by using bioplastics as an alternative to these petroleum-based plastic materials. What are bioplastics actually? Bioplastics are special types of biomaterials. They are derived from plant, animal, or microbial resources. They are synthetic materials but are sometimes criticized because their manufacturing and processing can sometimes lead to environmental impacts. For instance, if the bioplastic resources are needed to be cultivated, like starch or cellulose, then the cultivation can lead to environmental impacts. Other environmental impacts would include pollutants emitted from these crops that are needed to be transported to manufacturing facilities. With all those aside, I propose a big solution to these problems. It is something that everybody knows about. Probably people have thought about it but just shrugs it off. Fish scales. We can use fish scales as a resource of novel recycling. With its 200 nautical miles, an exclusive economic zone, New Zealand's remote and pollution-free environment is a home to a wide variety of fish. The commercial fishery consists of over 80 species, in which the fish scales are considered as scraps and waste products. But these so-called scraps have a lot of potential uses, and one of which is a source for material for a successful polymer. The large diversity of fish species also results in varying fish scale size, shape, structure, and composition. However, all of these fish scales include an internal partially calcified layer called the basal plate, and this basal plate is mainly composed of type 1 collagen proteins. Extraction of pure collagen from fish scales is still an ongoing research and have not been perfected yet. However, present methodology like demineralization and acid or pepsin solubilized methodology provides sufficient collagen amount and purity for creating a successful bioplastic. Although collagen is widely used in cosmetics, skincare, or food and medical applications, I formulated a series of ideal processes to create a successful bioplastic from this fish scale collagen. Type 1 collagen has a very rigid structure. It is generally hydrophobic and can exist in a certain range of pH and temperature. These collagen molecules then align them along a helix axis and group as a bundle of collagen fibers called fibrils. The fibrils are stabilized by covalent outer crosslinks, which is a carbon-to-carbon bond. Helix fibril formation is also aided by disulfide bonds between nitrogen and carbon terminal ends, which align the polypeptide chains in register. Via chemical denaturation, gelatin can be converted from collagen, and polymerization of gelatin is the primary methodology in creating polymer from fish scales. However, this process is chemically hazardous to the proteins themselves, as it wears out its structural properties. Such process is done by boiling the collagen to induce partial hydrolysis, creating gelatin which has similar structure to collagen, but with less arranged structure and with lost hydrophobic residues, hence losing the water-resistant properties needed into creating a successful bioplastic. Therefore, my first proposed methodology is to create a polymer using cross-linking techniques, heat treatment, and pressurized gyration. Cross-linking occurs between the collagen fibrils. There is some covalent cross-linking in between the triple helices and very little cross-linking in between the collagen monomers, which we call tropocollagens. Collagen fibrils are arranged in different combinations and concentrations in various tissues to provide varying tissue properties. However, in bone and fish scale, the collagen is arranged in a staggered parallel array. And these arrays have gaps, and the gaps in between them are nucleation sites in where deposition of long, hard, fine crystals of mineral components are added. And these crystals give the stable and insoluble properties of the collagen polymer. Type 1 collagen mainly gives tensile strength to fish scales. There are several syntheses on how this cross-linking occurs, but they are divided into two categories. The first is non-enzymatic treatment and enzymatic treatment. Enzymatic meaning there should be an enzyme which induces the bonding of these cross-linking chains. By controlling the enzymes added to the solution of the collagen polymer, then we can control the structure of these polymers. Heat treatment also allows reforming the collagen into shapes, as petroleum-based plastics do. As the cross-linked chains of collagens are being heated, their tensile strength increases with fluctuating temperature, also increasing the polymer's flexibility. Pressurized gyration is a new technique used in to increase the polymeric properties of nanoparticles. This uses centrifugal force in inducing bonds in between the cross-linking chains of collagen polymer. This would be very helpful in increasing the durability of the collagen polymer. However, large-scale pressurized gyration would be expensive in relation to the amount of residues and materials needed to be used. That is why I propose another way of creating bioplastic from fish scale collagen, and this is by mixing it with an existing bioplastic or an existing petroleum-based plastic material. An alternative to chemical denaturation is by the use of inter alia enzymatic pre-treatment methodology to induce partial hydrolysis. The collagen is pre-treated with protease enzymes, which catalyzes hydrolysis, followed by alkali and acid treatments to remodify the gelatin structure. This process produces gelatin at a shorter span of time and also allows us to monitor how much product we are producing. In this case, the inter alia treatment would be one of the best techniques into mixing an existing bioplastic or an existing petroleum-based plastic with the fish scale collagen. Cross-linking chains of collagens are made from nitrogen to carbon bonds. By controlling the acid treatments and the enzyme treatments, some of these bonds could be broken. Then plastic monomers could be added. For example, PHBV, which has carbon terminal ends, and starch monomers, which also has carbon terminal ends, which are susceptible to bonding. Once we add these monomers into the solution of the collagen fibers and control the enzyme and acid treatments, we can induce bonds in between the monomers of existing bioplastics, existing plastics, and the monomers of collagen fibers. Strengthening processes, which also includes heat treatment and pressurized gyration, could also be done after this process. The end product would be a strong polymer made from waste plus existing plastic polymers. This would have an increased strength because of the insoluble properties of collagen, plus the decrease in degradation time of plastic materials. A final plastic test could be done after the production process to test the durability, flexibility, and biodegradability of the bioplastic formed from fish scale collagen. These bioplastics can be used as plastic bags, cellophane films, disposable packaging films, and food services items. This project complies with most of the principles of green chemistry, as green and safe procedures are adopted. No hazardous byproducts are given out during the production, And the energy used in this process is not that high since the temperature needed are not generally high as well. The plastic material formed would cause minimal pollution to the environment because of the less degradation time in compared to the petroleum-based plastics. In short, these plastics are prone to be developed as the next frontier in the foreseeable sustainable future. When you think about it, collagen is used to beautify the skin, to repair breakouts, and to rebuild, and now also used in organ transplants. It is something that we use to enhance our beauty, to keep us alive and well. But as I have explained to everyone, collagen can also be used to beautify the environment, to keep our mother nature looking young, to repair, and it is possible. This one solution is right in front of us. We just need to grab this opportunity and start working on it, continue the research, and improve the ideas. This will create a whole new industry for the country and not only give profit, but the opportunity to reuse the waste by novel recycling. And now, instead of putting the plastics into the oceans, we are taking them from the oceans. We are going to use these resources for our benefit, and in turn, we can look back and tell ourselves that we have done well. We have prepared a clean environment for the future generations. That 450 years that a plastic bottle would spend in our environment would just be 450 years of recovery, maintenance, and improvement.
Thanks, Rochelle. Where do we get our collagen from now?
We get our collagen from bones of pigs and from the skin of animals as well.
So why don't we just use that for the plastics? Why do we need to go for fish scales?
Because fish scales are waste products. We don't use them for anything else. And if we get them from pigs, then we need to have another treatment for it. But the fish scales are right in front of us. They're actually free. So we don't need to waste money, but
no,
yeah.
I understand.
So it's actually waste, yeah.
Have you done any calculations of what quantity of fish scales you would need to produce what quantity of plastic?
I haven't done that much calculations, but from the fish scales, we can actually get 50% of it, of one fish scale has collagen in it. And by that, yeah, I haven't done that much calculation, but we're getting just as much. Because extraction of pure collagen from fish scales have not been perfected yet at the moment. Yeah, so I couldn't make a calculation yet.
You're not worried that it would just put more pressure on the fish stocks that are already under pressure?
I don't think so, because as I have said, these are waste products. We just throw them back to landfills and oceans. We don't really use them. So I'm thinking that shortcut, because they're biodegrading now, these fish scales. So I was thinking if we can use this for our benefit, instead of just throwing it as trash, we can manipulate this and use this for our own benefit to help the environment as well. Yeah.
And I may have missed this piece of information, but how long would it take such a product to biodegrade?
Oh, the fish scale?
Yeah.
Yeah, the fish scale takes about 50 days to biodegrade.
If you turned it into plastic?
If you turn it into plastic, then it would take a shorter time because we are breaking these bonds by creating plastics from it. So we are breaking bonds and creating bonds with it. So as a plastic, I think it would still take about 50 days, but by mixing it, because another methodology is by mixing it with another existing plastic. So it would be longer, but it would be less than the pure petroleum-based plastic.
Because people don't want their plastic to certainly not be there anymore, right?
Yeah, no sense in, if it's like that.
Thank you.
Yeah.